Well, I'm sorry we don't have a fun balloon activity this time like we did last time, but lots more drawing this time at least. Okay. So, one of the major reasons that we talked about the shape of molecules and the angles that those bonds form is so that we can predict whether or not the molecule will be polar. So, we talked about polar covalent bonds, where if there's a difference of electronegativity of the atoms in that bond, the electrons will be pulled to one direction, right, towards the more electronegative atom in that bond. But if there are multiple polar covalent bonds, those dipoles can add together geometrically to form a net dipole moment for the molecule. So those arrows pulling directions, we're going to add those arrows together sort of in 3 dimensions, and that'll allow us to think about, as a molecule as a whole overall, are electrons being pulled towards one side of that molecule or the other. Okay? Molecules with a net dipole moment are polar. Molecules with no net dipole moment are nonpolar. So as you'll see, it'll be possible for us to have polar bonds, but if their net dipole arrows are in opposing directions, the molecule overall could be nonpolar. So we'll look at how that works. So let's draw water. If we were just drawing it flat without any shape, we draw it like that. But because it has 4 electron groups, the electron group geometry is called what when it's 4? When you get 4 balloons tied together, what do we call that? Tetrahedral? So if we draw the OH bonds in the plane of the paper, what we'll end up with is a lone pair coming out towards you and one going back away from you. So let's just make it like that. Even though these aren't actual bonds, we just can show them like that sometimes to precisely show the direction of a lone pair of electrons. Okay? So, periodic table. What is more electronegative, O or H? O is, yeah. O is the second most electronegative element. Okay? H is somewhere in between boron and carbon over here, by the way. Okay? So, because of that, O is more electronegative. That is a polar covalent bond that way. Okay? Another thing that we can also do when we have a lone pair of electrons, because that's just pure electrons over at that end, we can also imagine there are little dipoles pointed towards the outside part of the lone pair of electrons. Okay? That ends up being a polarization of electrons as well, because there's 2 electrons here and less down in there. Okay? So what we end up with is a tetrahedral electron group geometry, so 2 in the plane, 1 towards and 1 behind. To figure out if this molecule is polar or nonpolar overall, we will add those arrows up. Okay? If you've taken, if you started to take calculus or sometimes advanced algebra or something like that, you talk about adding vectors. A vector is just something with direction and magnitude. And we can do that in 3 dimensions as well. It works really well with forces going in different directions. If you're pushing or pulling something from different directions, the overall force is the sum of those vectors. So you can sort of see that all 4 of these sort of have something in common with their directions. Okay? So if we added up all 4 of those arrows, what would the resulting arrow be pointed? Point with your finger. Yeah. Yeah. I mean, just these 2 would add up to one like that, and then just those 2 add up to another one like that. So it's all going to add up to an upwards pointing arrow. That's the sum, and we call that the net dipole moment. It's just the sum of bond dipoles. Okay? And because this molecule has a net dipole moment, that makes this molecule polar. Okay? So water's polarity is one of its most important properties. Okay? Water, it turns out, is extremely polar, and that's what makes it so unique in terms of the substances we can think of. Okay? So for a really common substance, water is very, very polar. All right, so let's draw CO2. We could add those up if we wanted. All right. 2, 4, 6, 8, 10. Yeah, did I add that up right? No, I just did the sixes. Okay, I was running out of dots there. 16. Helps to be able to do arithmetic when you're doing these. Okay, 2, 4, 6, 8, 10, 12, 14, 16. But what would make this better? Yep. Probably better make those double bonds. That will give the central atom an octet while still keeping all the formal charges as 0. Okay? Now, there are how many electron groups on this central atom? Remember how we count electron groups? Any type of bond, whether it's single, double, or triple, is an electron group, or a lone pair of electrons. So 2 electron groups on the central atom. So just on the carbon, there's a double bond which counts as 1 electron group, and another double bond which counts as 1 electron group. Okay? That was tetrahedral electron geometry. By the way, what is this molecular geometry called? Bent. Okay? When there are lone pairs on the central atom, the electron group and the molecular geometry are different. Okay? But no lone pairs. What is this geometry called with just 2 electron groups? Linear. Okay, so that's why let's not draw CO2 like this. Okay. The reason water is at an angle like that is because there are lone pairs on the central atom that take up their own space, but this carbon only has those 2 double bonds that repel each other. So they'll be straight across from each other 180 degrees. Okay? So, 2 electron groups. O is more electronegative than carbon. Okay? If those arrows are vectors, meaning they have direction and magnitude, okay, their magnitudes will be the same. Okay? That'll be the same strength pulling because it's both O's pulling from that carbon. Okay? So those arrows will be the same strength. Their directions are completely opposite each other. So what do 2 vectors that have equal magnitude but opposite direction do when you add them together? They cancel each other out. Okay? These vectors cancel, which means there is no net dipole moment. Which means the CO2 molecule is non-polar. just add this, equal magnitude, opposite direction. Okay. So, because of the bent shape, those did not cancel, and also because of the lone pairs, they have their own dipoles to them. That makes the water molecule quite polar, but the CO2 molecule is non-polar. CO2, condensed CO2, is sometimes used as a dry cleaning solvent. It's very non-polar, and it dissolves other non-polar things like greases and oils and stuff. So it can get clothes clean of the greases and oils, okay, without using a harmful non-polar solvent. Okay. BF3, still a pretty interesting one. What was the special kind of funny thing I told you about boron before? Yeah. 6 electrons, or 3 single bonds. And it's perfectly fine that way because this structure has 0 formal charges. Okay? That's really the main reason why. If we were to donate a pair in to try to complete its octet, we've actually made it worse by having a minus and a plus formal charges, or plus and minus, yeah, which it doesn't want to be. So, 3 polar covalent bonds, again, equal in magnitude. But now they'll be spread 120 degrees from each other. What was this shape called? Trigonal planar. Okay. Is BF3 polar or nonpolar? Okay. Because there's 3 of them, planar, 120 degrees apart from each other. Those cancel out. Okay. Just because they're equal magnitude doesn't make them cancel. These ones were equal magnitude too. Okay. But I make a big deal about equal magnitude because look at this structure. Chlorine is less electronegative than fluorine. So any ideas as to how we might indicate that? Plus arrow? No, it's not going to go towards B. Chlorine is still more electronegative than boron, just not as much as fluorine is. So it's still going to be an arrow pointed towards chlorine, but what, is it going to be higher magnitude or lower magnitude? Yeah. So one way of showing that might be drawing a short arrow. Correct. Fluorine is the most electronegative element on the periodic table. So any element will be less electronegative than fluorine. Okay. So, in this case, there's going to be a net dipole moment that's going to point, let's see here, it would be 0 if this were pulling totally. So it's going to be northwest. Going to be small, but yeah, separate these ones. So even though the angles are the same, 120 degrees, okay, those three equally spread out angles like that will only cancel if their magnitudes are equal. Okay? Think of that as I don't know if they have three-way tug of wars or something like that, but if you've got two really strong people and one weak person, the center is going to go in the direction opposite the direction the weak person is pulling. Right? So that makes that molecule polar. It'll be slightly polar, but still polar. This molecule over here non-polar. Does that make sense? Okay. CH2, F2, it's tetrahedral. Okay. Now, it's only considered a polar covalent bond if the electronegativity difference is over a certain point, it was 0.4 or something like that. Okay. It turns out that C and H are within that range that they can be considered similar. Okay? So the CH bond is a non-polar covalent bond. Okay? C is like 2.5 and H is 2.1 or something like that, so they're right sort of on the borderline. But for practical purposes, we do not draw dipole arrows on CH bonds. Okay? Their electronegativities are just too similar to really make a difference overall. So, don't draw arrows on those. Draw dipole arrows on those, however. It is very important you draw this kind of molecule tetrahedral, right? Because that adds up, if we just sort of split the difference, it's going to be like that. Okay. If you draw it that way, you can really clearly see how the molecule is polar. They'll have an overall abundance of electrons being pulled over toward this end of the molecule. If you're being a little bit careless about how you draw your molecules, though, if you drew it like this, can you see how you might get the wrong answer? So, the CH2F2 molecule is not square planar, it's tetrahedral. You might mistakenly think that the CF bond arrows would cancel if you drew it like that, but anytime you've got a carbon with 4 bonds, if you're determining whether it's polar or not, it's very important that you draw the molecule tetrahedrally so that you can see how those bonds actually interact. Does that make sense? Let's make carbonate. A couple of you learned this lesson the hard way, especially if it has a charge there. What's really important you do before you even draw anything? Yeah, you really got to add these up and then add those 2 electrons onto it. So 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So what should I do? Out of electrons for my C. Yep, let's double bond one of them, doesn't matter which. 0, 0, -1, -1. Adds up to the 2 minus, so we didn't make a mistake. That's good. I cannot donate any more electrons into that carbon because, why? Yep, carbon must obey the octet rule. Elements in period 2 cannot expand their octet like period 3 and beyond can. If that was a sulfur or a phosphorus or something, we could make additional double bonds into it to reduce our formal charge, but carbon must not exceed 8 in its octet. Okay? So that's good. But there are two other equivalent resonance structures. What's different about the, or how could we draw this differently to make an equivalent resonance structure? Yeah, there are 3 equivalent resonance structures. Just involving the double bond placement. Okay. So, even though this particular one has actual minus formal charges on those O's, okay, we would have a something like that, and that. If that was all we were talking about, a full minus formal charge is going to be a stronger dipole than just that. But the 3 equivalent resonance structures means those CO bonds are going to all be the same. They're all going to have partial minus, equal partial minus on all 3 of those O's. Okay.
So when you try resonance structure like that, you can't really put in the electrons very well.
When you're drawing a hybrid, we're no longer specifying where actual electrons are, but this is actually more accurate because in the real structure we don't have 4 electrons here and 2 electrons here. We got somewhere in between, distributed equally through all of them, it turns out. It's just this is convenient for us on our octet rule and stuff to make sure that our structure is drawn with the right number of electrons, but we have to blend this with the double bond here and the double bond here when we're talking about the properties of the overall structure. Okay? So, because all of these CO bonds are identical, that would make the magnitude of those dipoles also identical. And that would do what to the net dipole moment? Yeah, this has no net dipole moment. Okay. Now, I'm not going to go as far as to call it nonpolar because it actually carries a charge to it overall. Okay? So, I mean, it's a little different from the other nonpolar molecules that have no charge. But the charge that it carries is distributed symmetrically through it so that there's no net dipole moment, it turns out. Okay? So, questions about those? If the question is this molecule polar or nonpolar, you need to draw it with its correct shape. Okay? Get all the geometry correct because you're going to go in and look at how these bond dipoles either add up to a net dipole moment or cancel each other out. Okay? That's how you determine if that's the proper way of determining if a molecule is polar or nonpolar. Okay? So we got plenty of practice in that in the Mastering Chemistry. This due Wednesday. That's probably what most of the Mastering Chemistry will be about. Okay? Were there any other questions about any of these?
Does the double bond affect the dipole movement?
Nope, I don't think so. The analogy I use for my intro chemistry students is that it's if you're imagining a tug of war and you've got a strong person and a weak person, the tug of war isn't going to be changed by putting 2 ropes in between those people or 3 ropes or something like that. It has to do with how hard they're pulling. So the pulling force comes from the difference of electronegativity in those atoms themselves and is sort of distributed that way no matter how many electrons are actually being pulled by it. Okay? So,